we have been discussing about vibrations of plates. So, we have looked at the rectangular and the circular plates in our previous lectures. Today, we are going to discuss some special problems in vibrations of plates. So, before we do that, now as you have seen in the previous lectures that even for some simple problems, the analytical solution becomes very complex, and sometimes with increasing complexity of the geometry or the boundary conditions, etc., the analytical solution becomes intractable. So, in such situations we would like to have approximate methods for discretizing the dynamics of plates and performing modal analysis, which we obviously expect them to be approximate, but then with we can, there is always a scope of improving the accuracy of these methods, and we have seen such approximate methods in this course. So, today we are going to look at two examples based on which we are going to solve using the approximate method. So, before we start discussing the examples, let us look at the variational formulation of plate dynamics. Till now we have not discussed this variational formulation. We have discussed only the Newtonian formulation of plate dynamics. Now, this variational formulation is a little cumbersome for the plates. So, let us see how it is, at least how it is formulated. But then if you go through the variational formulation of plate dynamics, then you will also see that the boundary conditions are obtained naturally in the process. So, you can cross check that the boundary conditions that we have discussed based on the Newtonian formulation and based on von Karman's boundary condition for free edge, you can obtain them directly from the variational formulation. So, let us start with a little bit of discussion on the variational formulation for dynamics of plates. So, let us consider a plate now here. So, when we do the variational formulation, we first write down the kinetic energy of the plate. So, the kinetic energy is for this little element is given by 1/2. If rho is the density, then dx dy dz, where z is the coordinate perpendicular to the plane of this figure, that is plane of the paper. So, this is the mass of this little element times its transverse velocity square. Now, in addition, if you also have if you want to consider the rotary inertia, then you have, in addition to this, 1/2 rho. Now, this is the this is the mass times z square. So, mass times the distance from the neutral plane square. So, that will give the moment of inertia of this little element at height z from the neutral axis times the angular velocity square. So, now angular velocity can be written as in the y, it is written as del w del x del t of del w del x whole square So, this is the contribution from the rotary inertia, and if you now integrate this over the complete volume of the plate, then we can obtain the total kinetic energy of this plate. Now, since this field variable tracks the transverse displacement of the neutral plane of the plate. So, this is independent of z, and if the density is uniform etc. So, with all those nice conditions. So, there is nothing in the integrand that is function of z. So, z can be integrated out and written So, z goes from minus h by 2 to h by 2. So, this z coordinate goes from minus h by 2 to h by 2, where h is the thickness of the plate. So, then if I perform that integral, I can simplify this expression. So, is the integral over the area now of the plate. So, that is the kinetic energy. Now, this I, which is the moment of inertia of per unit area, so that is the moment of inertia per unit area of the plate. Next, we will write down the potential energy expression. Now, we have considered that this little element is subjected to in plane stresses. So, if you have this in plane stresses, then the strain energy stored because of the deformation is given by half times stress times the strain. So, now we have the normal stresses times the strain in the x plus normal stress in y times strain in the y, and plus 2 times the in plane shear stress and the corresponding shear strain of the element. Now, this is per unit volume. So, now I have to again integrate the thickness goes from minus h by 2 to h by 2, and x y go over the domain of the plate. Now, here I have to finally obtain these expressions in terms of the displacement field variable, which is W. So, to do that, we first write down the constitutive relation, which is the Hooke's law. From Hooke's law, we can write, we have seen this before. So, the stress, normal stress in terms of the normal strains in x, similarly in y, and the shear stress in terms of the shear strain. So, if you use these expressions in the potential energy and of course, we also have to write these the strain displacement relation, which we have also written out before. So, from the displacement kinematics, so we have seen these expressions before. Now, so we will substitute these strains in terms of the displacement field variable in here, and finally, the stress terms will be put here. So, if you do that and make the final simplification, then upon integrating over the thickness direction, so this is the expression of the potential energy, the strain potential energy, where this d is here, of course, E is the Young's modulus and nu is the Poisson ratio. Now, so with the obtained expressions of kinetic and potential energy, we can now write the use the Hamilton's principle to derive the equation of motion. So, Hamilton's principle says that this variation must vanish. So, we have these expressions of the kinetic and potential energy, and if you want to derive the equation of motion, then you must follow the procedure that we have discussed in case of other structural elements like strings, membranes, etc. So, this will closely follow that of the membrane, only that the terms are more complicated complex here, and because of that the procedure is straightforward, but cumbersome. So, one can derive the equation of motion, and the boundary conditions are also obtained along with this. So, that is the advantage of using the variational formulation. So, now using this, then we can also use the discretization using Ritz. So, based on this Hamilton's principle and Ritz expansion. So, Ritz method requires the Ritz expansion plus the Hamilton's principle. So, these two lead us to the discretization of the dynamics. So, let us look at two examples. So, the first example that we are going to discuss today is that of a square plate supported on a circular boundary. So, let us look at the geometry of the problem. So, suppose this is a square plate of uniform thickness, which is supported on a circular support. It is simply supported we consider that the length is 2L and this is at the geometric center. Now, so we are looking at square plate on a circular support. This radius of this support circle is A, and the side is 2 L. Now, we already have the kinetic and potential energy expressions, but I will make some simplification, some non-dimensionalization. So, this x coordinate is non-dimensionalized with respect to the half length of the plate. Similarly, the field variable w, which tracks the transverse displacement of the neutral plane, is also non-dimensionalized with L, and we define a non-dimensionalized L tilde. Now, time is also non-dimensionalized in this form. Now, so with this non-dimensionalization scheme, the kinetic energy, if we will consider an Euler-Bernoulli plate, the Kirchhoff plate. So, we will consider a Kirchhoff plate. So, in the Kirchhoff plate we do not consider the rotary inertia terms. So, the kinetic energy expression simplifies. So, these are all simplifying assumptions. I have dropped the tilde for convenience. So, here now x and the y coordinates go from -1 to +1. Similarly, the potential energy expression So, that is the potential energy expression for the plate. Now, let us look at the support condition. Now, in the we will be using the Ritz method. The advantage of this method is that you have to generate only admissible functions for the problem. Now, we know that when this is simply supported, the only condition at this boundary is that the displacement is 0. So, if I parameterize this circle using this angle phi, then this is the boundary condition. In terms of x y, I can write So, I can write in any one of these ways. Now, we will what we have to do is we have to write this as an expansion So, there will be of course, two indices in this form. So, we have to write the solution as an expansion in terms of some known functions. So, these are our admissible functions. Which need to satisfy only the geometric boundary conditions of the problem, and this boundary condition is the geometric boundary condition. So, we have a geometric boundary condition in this problem, and of course, there is a natural boundary condition also, but and on this. So, here on the edge these are free edges. So, we have again natural boundary conditions at the free edges. Now, so what could be a good choice of admissible functions for this problem? So, let us see if you have suppose you choose W11, the first term in this expansion, as this. Now, you can see of course, that on this boundary this is going to vanish. So, then I can generate the expansions here as multiples of or products of this function and other monomials. Say x power m and y power n. So, I can think of this construction, but before we do the general situation, let us look at only a one term expansion and do the Raleigh's determine the Rayleigh quotient. So, we are going to determine the fundamental frequency of the square plate which is supported on this circular boundary. So, this the non-dimensional frequency square then turns out to be So, this is the assumed eigenfunction for the fundamental mode, which we are assuming in this form. So, this is going to be the Rayleigh quotient. So, if you substitute this as the assumed mode shape function in the quotient, then this turns out to be, if you perform these integrals, so I have kept this A as it is. So, I have not assumed any particular value of A. Now, we may then think of, for example, improving the support. By improving the support, I mean that increasing the natural frequency of the plate. So, if you so here of course, this is the non-dimensional frequency. So, the dimensional frequency will be obtained using this expression. Now, if you want to improve the support, so suppose you want to ask the question that what should be a good radius for support, this circular support, so that the plate is well supported. In that case, what we are asking is what radius will give a very high natural frequency. High natural frequency would mean the support is quite stiff. So, what would result in a very high natural frequency? So to do that, so you can make this stationary with respect to A, and that gives a value of optimal radius as square root of 2 over 3, and corresponding to this, the optimal, the max. So, basically this is maximum. You can check that by taking the second derivative. This is actually maximized. Which can be checked by taking the second derivative with respect to A and looking at the sign of the second derivative. So, this happens to be the optimal non-dimensional radius. Now, let us go back to our Ritz discretization problem, and now we can take this optimal radius and discretize the problem. So, the expansion that we are using so P, these are the coordinates, and that multiplied by the admissible function. So, this is an expansion which we will substitute in the Hamilton's principle. So, we will calculate the Lagrangian So, that is obtained as an integral over the area, which now is actually dx dy. So, we will integrate over x and y to obtain the Lagrangian. Now, since we know all these functions and these are polynomials, so it is very easy to perform this integral. So, we obtain the Lagrangian. See, this Lagrangian is a function of these coordinates and their derivatives. So, once we have that, we have actually discretized the problem. So, this Lagrangian will have this structure. So, the equation of motion will follow. So, that is straightforward. So, these are the mass and the stiffness matrices of the discrete problem. Now, if you perform this and do the modal analysis of this, then the natural frequencies, the first few of them, etc. So, you see these two frequencies are the same. So, there is a modal degeneracy. You can check that the eigen vectors that you will get corresponding to these two eigen frequencies are distinct. So, you will have from here you can construct back the eigen functions, and these will be orthogonal. Now, this figure shows the modes of vibration of the plate. So, this is the optimal radius, which happens to be around 0.8 non-dimensional value. So, the radius is 0.8. So, this is the fundamental mode. These two are the degenerate modes. As you can see that this is nothing but a rotation of pi by 2, which is the symmetry of this problem, because this is a square plate. Rotation of pi by 2 is not going to change the problem. So, you can see that this mode is rotated version of this mode and vice versa. Then this is the third distinct mode. So, these are degenerate modes. The second mode is degenerate. Now, it may be of interest to see what happens when A changes, when we vary A. So, this figure shows the variation of the first few non-dimensional circular eigen frequencies with A. So, this is the fundamental frequency of the plate with variation of A. So, you can see that the maximum occurs somewhere here. These are degenerate. There are two frequencies here, two modes corresponding to this branch, and this is the next higher mode, and then these are some further higher modes. So, you can see the variation of the eigen frequencies of the plate with A. So, we have seen how we can optimally support a square plate, or now you can attempt any other form of plate with a circular support and trying to find out the optimal support radius, for example. So, that gives the maximum stiffness to the structure. So, this is a very important problem in structural engineering. The next problem that we are going to look at is so we have a plate we would like to see what happens when a plate is having stiffeners. So, a stiffened plate. So, the vibrations of a stiffened plate. So, we consider again a square plate we consider that this plate is clamped on these two opposite edges. So, these two edges are clamped, so the coordinate system is located at the geometric center. These sides are 2a, and this is stiffened on these edges are free, but they are stiffened by beams. So, we have two stiffeners on these two free edges. So, this is the description of the problem. Now, let us look at the kinetic energy. So, the kinetic energy is composed of the kinetic energy of the plate and the kinetic energy of these two beams. We assume consider these plates to be this plate to be a Kirchhoff plate and this beams to be Euler-Bernoulli beams. So, the kinetic energy of the plate is given by this, and along with this we have two beams on these two edges. So, rho a is the mass per unit length times the length times the velocity. Now, this velocity is the velocity of this point. So, this has to be calculated at so for this beam at y equal to minus a, we consider identical beams. So, rho a is the same for both. So, that is the kinetic energy of the total system. Now, the potential energy again will be the sum of the potential energies in the plate and in the beams. So, so that is the plate part, and in addition to this we have, so everything being uniform, so this term brings in the strain energy stored in the beams. Now, once again to simplify these expressions, we use a non-dimensionalization. So, then the Lagrangian reads So, this is the potential energy of the plate. and this term is for the two beams. Now, for the admissible functions, we for the Ritz method. So, we will use once again the Ritz discretization. So, the admissible function, so this expansion is taken in the form such that the geometric boundary conditions are satisfied. So, in this problem we have the geometric boundary conditions only on these two edges, where the displacement and the slope they are 0. So, on these two edges we have the displacement and the slopes as 0. So, the geometric boundary so functions that respect this geometric boundary conditions, these geometric boundary conditions can be written as in this form. So, you can see that it starts with the quadratic in this x at both boundaries. So, that the slope, the displacement is 0 at x equal to 1 and minus 1 and plus 1, as well as the slopes are 0 at x equal to minus 1 and plus 1. So, if you use this expansion in the Lagrangian and discretize and finally solve the eigen frequencies, which are obtained as the non-dimensional numbers. So, the first few circular eigen frequencies are obtained like this, and the dimensional eigen frequencies are obtained from here. Now, once you have the eigen functions which are obtained once again from this expansion by calculating the eigen vectors of the discretized system. So, you can determine the modes of vibration of the plate. So, in this figure I have plotted these first 4 modes of the plate. So, you can see, so these edges are the clamped edges. So, the straight edges are actually the clamped edges. So, you can see the displacement, and of course, this displacement and slope will be 0 because the geometric boundary conditions have been satisfied. Now, here this is a stiffened edge. So, you can see that displacement here is maximum, here it is not so high. Had there been no stiffener, then this would have vibrated like a beam. So, the displacement here also would have been as high. So, because of the stiffening effect of the beam, we have lower displacement at these edges. This is the second mode. So, this is an asymmetric mode with one nodal line at the center. Here this is the next higher mode with 2 nodal lines, and here you have one nodal line parallel to the support. So, here you can see the displacement of the stiffened edge is very low. So, to summarize, we have looked at some special problems, 2 special examples of plate vibrations. So, we started off with the variational formulation of plate dynamics, which can be used to derive not only the equation of motion, but also the boundary conditions. Then we have looked at a square plate on a circular support and a stiffened edge stiffened square plate. So, with that I conclude this lecture.